Welcome, everyone. I'm Ankur, and here's my colleague Mingmin. We are here to share our journey where how we scaled Uber's infrastructure to about 1 trillion messages a day. To introduce ourselves, I'm a senior software engineer with streaming team at Uber, and I'm focused mostly on Apache Kafka. Before Uber, I was working at eBay, where I started with an 8-member team, which was building cloud, and we took it to 1,000+ nodes. I'm also a Kylin committer and PMC. And here's Mingmin.
Thanks, Ankur. Hi, everyone. My name is Mingmin. I'm also a senior software engineer with the streaming team at Uber. Same as Ankur, my work is also focusing on Apache Kafka and the system that we built around it. Previously, I was working on the distributed data systems at Twitter, mostly on Apache Hive and Apache Spark. And prior to that, I was an engineer at Team at Oracle.
All right, so for today's talk, this is what the agenda is. We're going to go through some of the real-time use cases at Uber. We'll discuss our scale in brief. And then we'll deep dive directly into our architecture on how we built this whole infrastructure, talking mostly about some of the critical pieces like REST proxy, local agent, and our work which went towards uReplicator. The next thing we're going to talk about is some of the special use cases like reliable messaging using at least once Kafka, and some of the tools that we have homegrown, which is Chaperone cluster balancing. And then we'll give you a sneak peek of what we are working on and what we might introduce the community to in coming future. If we talk about real-time infrastructure at Uber, Uber is mostly powered by real-time processing, be it matching riders with drivers, be it calculating the fares, be it doing like finding out ETA, sharing your status, everything and anything actually goes through real-time infrastructure. So let's go through some of the customer-facing use cases that you see every day. So if you think about our rider app and our driver app, they are emitting thousands or hundreds of thousands of data points every minute. They all go through Kafka. And then they are fed into our stream processing system, where we do meaningful calculations on how to match people up, what kind of ETA we are looking at, and then that's fed back to the applications. Here's another widely important use case. I know, how many of here has used Uber Eats? Cool. It's a very cool app. Please go and use it. We're partnering with many restaurants right now. But if you think of it from an engineering problem perspective, it's a very complex calculation to calculate any reliable ETA for food. The things that are involved is the restaurant which is preparing the food, how busy that restaurant is, what kind of dish you are going to order, how much traffic is on the road, how many cars are in that area. Everything and anything can affect your ETA. And what is going on right now is very important. So all these data points are being collected in real time. And then there's a machine learning model which is updating itself on the fly and giving you an ETA. Fraud detection, another big use case. Uber has a lot of fraudulent issues, and we need to find those out right now. Because if we are doing a processing a few minutes later, the trip has already happened. ETA, when you share your ETA with your friend, so think about the data points going into the system, being processed and shipped out to other people. And many more. I can go on and on. How do we do that? They're just two magical words, Apache Kafka. So I would go up to extending Apache Kafka is the hub of Uber's data. And by the way, how many people are here know Kafka very well? Oh, awesome. So, all our presentation from here on, we're just going to talk about Kafka. We're not going to go deep dive into like some of the very like how do we tune and other things, because we are trying to stay at least 1,000 feet above and talking about architecture and like big things. But if you have questions of which are pertaining to Kafka itself, just feel free to ask. All right, so what do we feed in Kafka? So Kafka is being used in many ways for us. We're using it as a general pub sub system. So any microservice or any of our application, they talk to each other using pub sub system. We already talked about some of the real-time processing use case. We use Samza and Flink and many other stream processing engines, which are fed by Kafka. Our Kafka also feeds into HDFS and S3 for most of our offline processing. And another important use case is database changelog. Last but not least, logging. So most of the volume of data being generated is logging, as you guys know. It's also going through our Kafka infrastructure. Let's talk about scale. And this is, by the way, our favorite slide anyways. At the current given rate, we're doing more than 1 trillion messages per day. And I'll give you a second to absorb that. So when I say trillion, we're talking about 10 million messages per second on average, where our peaks could be higher. So by the time I say word trillion, we've already processed like a few million of messages. And we're handling more than a petabyte of data per day. And there are tens of thousands of topics. And all this data, it's organic messages number. This doesn't include replication. All right. Here's an architecture diagram of how Uber's data stack looks like. If you look on the left side, that's where most of our data comes from. All the applications, services, and some of our databases. They all go into this one central piece, which is Kafka. From there, data is pulled by many other systems, like search pulls data to find out and do some fair calculations. Then Elk pulls the logging data to provide a real-time debugging dashboards to our developers. Real-time processing engines pull data for whatever calculations they need to do. And some of the data goes to S3 or Hadoop for offline processing. So just talking about this centerpiece, which is Kafka. When we started developing this system, these were some of the requirements we had. We wanted the system to keep growing as Uber is growing. So it was like you needed to scale horizontally, and you needed a very fast system where we wanted our client-side latency to be less than 5 milliseconds. Our availability has to be at least 4 nines because it being such a centerpiece. And our durability guarantees. By durability, I mean if you put X number of messages in, how many of those messages are available to be read. So the requirement we promise is 4 nines. Actually, we are doing about 5 nines. And that's for the general use case, including logging, where we are okay taking some loss. There are also some use cases like hypercritical data, like payments and finance, where we have 100% reliability. This architecture had to scale to multiple data centers, and it needed to support 5 different languages in which Uber's applications are written in, which is Java, Go, Python, Node.js, and C++. And we had to have a system in place which can audit all those trillions of messages going in to make sure that how much data we are losing, where are we losing it. And we're going to go in some of these in detail. So this is how our Kafka infrastructure looks like. At the center of this is our regional Kafka clusters. So this, by the way, for example, this is a picture for one data center. And we have similar thing for all the data centers. So if you see, this is where I would start looking at. This is where, this is the central piece of our architecture where we have Kafka broker or Kafka cluster in the middle. In front of that, we have our homegrown REST proxy clusters. Why do we use REST proxy? Because we wanted to decouple our applications from our Kafka clusters, and we'll talk about REST proxy in detail. Then we have our homegrown proxy clients, which are very tightly coupled with our REST proxy servers. Then, we have uReplicator. uReplicator is nothing but our version of Mirror Maker. So Mirror Maker has some problems, which we'll talk about as well. And we took and recreated the Mirror Maker. And then we take all that data from all different data centers and put it into aggregate clusters for the topics where you need the holistic picture of everything. We also have some customizations where we have secondary Kafka clusters. This is a fallback cluster in case our primary cluster, any of our primary cluster is having issues. A REST proxy can start buffering data into secondary clusters, from where, as soon as the primary cluster recovers, we take data back and put it there. We have local agent, again, something homegrown. We're going to talk about that as well. This is in case our REST proxy cluster is having an issues. Our proxy client can start writing to local agent and buffer the data there until the downstream system comes back. All right, one of the important things I want to highlight here to get to a scale that we reached, one of the very important design choice we made is very aggressive batching and async processing at each stage. Here's how life cycle of a data packet looks like. An application writes data to our proxy client, which is embedded into the application. The proxy client takes the message and acknowledges right away. It takes that message and puts it into a buffer where it can asynchronously produce downstream later. So what this gives us is very high throughput and very low latency. We can do like under 1 millisecond for each message. So that way there's no blocking, and you can produce as much like at the speed applications can handle. From there on, it is asynchronously produced to our proxy servers. Here, proxy server does exact same thing. It takes the batch and acknowledges right away. And then it divides the batch, splits it up into multiple different batches, depending on which broker they need to go to, and puts them into different batches to be asynchronously produced later on. Then, when proxy servers produces it to regional Kafka cluster, we use the setting of AX equal to 1. So same thing. So leader accepts the message and acknowledges. So the application can happen at its own pace. This way, we don't block, and we quickly return an acknowledgement saying, hey, okay, it is accepted. From that point on, uReplicator takes the message and puts it into an aggregate cluster. This part is okay because this is anyways happening asynchronously. But the overall highlighting point is at these 3 stages, we did a very aggressive batching, and we didn't block at all. That's why we can go at a lightning speed. And then at both of these clusters, these Kafka clusters, data is available to be read. All right, so let's discuss all this diagram in detail. Let's go one piece at a time. We'll start with the center again, regional Kafka clusters. So one of the main things, without going too much into depth of tuning for each cluster, but one of the things that we did is we have different cluster for different use cases. Why? Because not all use cases are same. Every use case requires its own kind of tuning. So for example, our data clusters, they need high throughput, but it's not as much throughput as our logging. But at the data, if we lose a data point, it's important because for downstream calculations, we don't want to lose the data. So we're okay blocking little bit, but losing a data, like we need more durability guarantees at data. For logging, we don't want to block at all. We want log to go like that, and hence it's okay to lose data, but not okay to block. For database change log, it's totally different story. You don't want to lose any data point at all, and your sequence also matters. For other use cases like search, stale data is useless. What you care about is what's happening now. So if you are having any issues, drop data, but recover fast. And then there are high-value data where it's okay to block for a long, long time, but don't lose any message. So what we did is we created many, many clusters, and we may have few clusters for data, few clusters for logging, and then we separate those pipelines. We have one secondary cluster to fall back. So that's in the hope that we don't have issues with more than one Kafka cluster at a time. And then we're running global aggregates. All right, let's look at the second most piece. First piece is not like the first thing that we discussed, which is regional Kafka clusters. Only thing that we did there is tuning. We haven't changed the Kafka code that much. But this point on, in this side as well as backward, is where most of our work went into. So Kafka REST proxy is something which we have invested heavily in. And one of the most frequently asked question is why REST proxy? Because the majority use cases, they directly use the clients provided by Kafka community and directly write to the Kafka cluster. In our case, we wanted to decouple our clients from the Kafka cluster so that if we're doing any maintenance, if they're having any issues, we don't impact the client. So that was one of the major reason why we went towards REST proxy. But the other important reason was, as you saw, we needed 5 languages to be supported. When we started building this infrastructure, there was only Java, which was first-class citizen in Kafka community. So we had to either write all those 5 clients, or we thought, let's write REST proxy and REST clients. Another thing is we built some of the important features for us. For example, primary and secondary cluster support. We built quota management, which was not there in Kafka 8. That's where we started. And then we have multiplexing, where a REST proxy can write to many clusters. Here is how we did it. We took Confluent's open source REST proxy. We tried it for our use cases, and we found that it can only scale up to 7,000 QPS per box. By the way, it's not the current number. This benchmark was done back in June of 2015. So we thought, okay, this is not going to work for us. And then we started working on its performance aspects first. We took out the Jersey layer and we replaced it with simple HTTP servlet. And Confluent's REST proxy is optimized for JSON. For us, we were supporting all sorts of things, so it didn't make sense for us, and we started taking bytes in and bytes out without parsing it. Just these 2 things increased our performance from 7,000 per box to 45,000 QPS per box. Then we did another improvement where Confluent's REST proxy was going to Zookeeper to fetch metadata every time there was a new topic request. We started caching that because we had thousands of topics and we couldn't afford to go to Zookeeper every time. And then we started putting more reliability aspects like fallback cluster, which I've already discussed, and talking to multiple clusters from the same REST proxy. We hope to we're planning to contribute this back to community whenever we can. This graph just shows this is how much we can scale on our REST proxy nodes, which is around 45,000. Next important piece is our producer libraries. Once we were done with REST proxy, we started writing these proxy clients and started with very simple API, but then we started putting more features in. First thing that we put in is the non-blocking async operations, as well as batching. We already have talked about it. Another thing that we did is we have backoff implemented in proxy. So whenever REST proxy downstream is having issues, it can send a signal back to proxy clients, and they can start backing off. Another important feature is, our proxy client can talk to many clusters. So you could be writing to like 10 different clusters from the same application without knowing about it. So we do auto discovery, we do metadata caching, and we can do multiplexing. And last but not least, if our downstream is having issues, our proxy clients know how to detect it and buffer locally using local agent, which I'm going to discuss next. All right, so let's talk about this guy. So local agent is one important piece in our infrastructure and something that we are very proud of. What we did is we used to have problems on REST proxy in early days, and that would cause back pressure on applications, causing either data to drop or them to halt. So we created a small, lightweight process by taking some of the code out of REST proxy, where we implemented the same REST interface, and then we take the heart of Kafka, which is log module. So we took both of them together, put them into one process, and created a lightweight engine that can run on all the nodes. So now this little thing is running on each and every box in Uber. Anytime our downstream has an issue, it causes a back pressure here. Our proxy client realizes that, they start putting data to local agent using the exact same API, and local agent puts it on the disk and waits for the downstream to recover. As soon as it recovers, it slowly start backfilling. So here's one of the examples. This is the very first time local agent came into action after we had created it. We had about 1 hour of outage, which started around 8:10 and ended around 9:10. This graph here shows our REST proxy cluster showing that traffic dropped to 0 around 8:10, and it recovered around 9:10. So if you think about it, the Kafka was down for 1 hour, right? And at that time, this graph here shows all our local agents are reporting that they see some traffic, right? So data started going there locally, and it started, putting it on disk. As soon as around 9:10, the traffic on local agent drops while it picks up on REST proxy. And around same time, around 9:10, the local agent starts writing the data back to REST proxy, and at certain point, it's done. And this bump shows, regular traffic plus some local agent traffic. All right. Now onto our last piece, uReplicator. We started using MirrorMaker to get data from different DCs and put it into aggregate cluster, which is the natural choice, and most of you are already using it, which is fine. But we started seeing some issues around between 5,000 and 10,000 partitions per cluster. So when MirrorMaker is handling so many partitions, anytime a broker goes away, broker from which it is reading, or a partition moves, or partition is deleted, MirrorMaker takes all the resources, all the partition, and rebalances all, which takes few minutes, like 10 to 15 minutes for all rebalancing to finish, and which suddenly became a big issue for us. So what we did is we took the rebalancing portion of MirrorMaker and replaced it with Apache Helix-based resource management. And since then, things have been fine. and we have scaled it to 10x compared to where we saw the problem. We are running uReplicator for last 2 years. It's open sourced. If you guys are using mirror makers and facing this kind of problem, feel free to give it a try. Now Bingmin will walk you through some of our special use cases and tooling.
Thanks, Anka. So we do a bunch of cool stuff around reliable messaging and tooling. And the first one I would like to share with you is, at least once, Kafka. So the Kafka pipeline Anka just showed you is good enough for most of the use case, but it's not good enough for some hypercritical data use case. For example, payment. They need 100% durability guarantee. That's why we build this at least once Kafka. So as you can see in this data workflow, we are doing batching in each stage. And in case anything happens to the, say, for example, application crash for some reason, the in-memory batch may not be delivered to Kafka. Or anything happen to the proxy server, if a proxy server just crashed for any reason, then it may cause any data loss. Similar thing will happen to regional Kafka cluster. We tune in a way that it will acknowledge to proxy server once the leader replica receives the data. But what if the leader replica went down? Then the data will be lost. Same thing will happen to aggregate Kafka cluster. Leader replica will lead to data loss if anything happened to the leader. And that's not acceptable for high-value data like payment. So we tune our workflow, data flow a little bit. So first of all, we change our proxy client in a way that it will send the data in the synchronized way to Kafka proxy server. And proxy server will skip the batching stage, and it will just pass through the data to regional Kafka cluster. And we also tune the regional Kafka cluster in a way that only when 3 of the replicas receive the data, it will acknowledge back to the proxy server, and then proxy server will send the acknowledgement back to the application. We also tune the aggregate Kafka cluster in a way that only if 3 replicas receive the data, it will send back the acknowledgement, which means we have 100% data durability guarantee for the regional and aggregate Kafka cluster. But as you can see that the latency will be increased a little bit higher than the general use case. Basically, we are trading latency for durability guarantee, which makes sense for the high-value data. The next thing that I would like to introduce you is the auditing system that we built in-house. We call it Chaperone. So Chaperone is a auditing system that we plug in each stage of the pipeline. We have audit library in the proxy client and proxy server, which will basically do the message counting for every single topic in every 10 minutes time window. And then it will send the metrics to Chaperone web service, which will then aggregate those metrics and send them back to Cassandra database, which is running across multiple data centers. We also have Chaperone Kafka service, which will consume all the messages from regional and aggregate Kafka cluster and do the counting similarly for every single Kafka topics in 10-minute time window and send the metric back to Cassandra database. And then Chaperone report service will do the comparison for all the 10-minute time window across different stage and compare the count and generate the data loss report and latency report. One thing to note here is we are using the same time stamp in the message itself across different stages, such that we can guarantee the accuracy for the Chaperone report. Here is a dashboard that is reported by Chaperone, which basically just check the message count across different stages across the pipeline. As you can see on the top graph, the message count matches exactly for different stage, which means we don't have any data loss across the time window. And on the bottom graph, as you can see, we are having some mismatch in this small time window. In the proxy client, it reports around 80K messages, but proxy server reports around 50K, which means there are something going on between these two stages. And it will basically trigger an alert to our on-call, and then we can look into the issue and fix it. Here's another dashboard that was generated by Chaperone, which will check the latency of the messages across different stages. As you can see, the latency can be checked across different stages. And it also will trigger alert in case it's violating our latency SLA. Just to summarize, we built our in-house auditing system for Kafka, which we call it Chaperone, which is running in production for around 2 years. And it's auditing tens of thousands of topics for 4 nines completeness guarantee. And it's already open source and blocked. Please take a look if you are interested. One thing to note that is that the open source one is an older version of Chaperone, and the one that I present is a newer version that we plan to open source in the future. All right. So next thing I would like to introduce you guys is the Kafka Cluster balancing tool that we built in-house. Some of you may know that running a very big Kafka cluster may run into some issues. One of the issues is Kafka doesn't have balancing by itself. So as shown in this graph, a node here in this graph means a node in the Kafka cluster, and an edge between two nodes means the data share by replication. And in this graph, it shows that some pairs are sharing small amount of data, but some other pairs may share like big amount of data, which means this cluster is not well balanced. And so we built our in-house cluster balancing tool, which will generate a partition moving plan. And then after execute this moving plan, it will make this cluster well balanced. As you can see in this graph, this cluster is after we run this balancing tool, and it's well balanced. The data share between each pair is more or less the same. All right. I also want to talk about some of the ongoing work and future work that we are doing. So the first one is multi-zone Kafka cluster. we basically deploy a single Kafka cluster across multiple data centers in a way that the data can be written to multiple data centers consistently. So in case there's any data center outage happening, we can still guarantee the durability. That is really helpful for some high-value data. And the second one we are working on is chargeback. We are basically accounting all the resources used by different producers and consumers, and we can generally report for different topics and different teams, which is really helpful for us when we do resource planning. We are also working on some efficiency enhancement. For example, topic garbage collection. Some of you may know that Kafka itself doesn't do garbage collection for the inactive topics. And we are running into some of the issues that some topics are inactive for a long time, which is taking the resource for the cluster. So we built this garbage collection tool, which will collect those inactive topics and clean them, which is really useful for the resource cleanup. We're also working on some uReplicator enhancement, which we plan to share the learning to the whole community. We're also working on some open source that around the tooling and different projects that we are doing at Uber. So stay tuned. We will open source more of these cool projects and much more. With that, concludes our presentation.
Yeah, no, we haven't left too much time for questions, but still, they're welcome. So we can start over there. Yes.
So can you elaborate on the process
I'm sorry, I can't hear you. So why don't we move over here while.
So the disk balancing, right? So the balancer works at the node level or at disk level?
So it is at disk level. The way we do it is we look at the partitions on each node, and we try to figure out how much that partition is occupying on that disk. And we do that for all the nodes and all the partitions, right? It's like a scheduling problem. So we try to come up with a plan which is ideal by only moving replicas, not moving leaders. And then that generates a plan which we feed to the Kafka rebalancing tool, and that it runs.
As you said, is it your own custom build or using
So the rebalancing algorithm and like collecting data, rebalancing algorithm is all built by us. And then output is a JSON which we can feed to the Kafka's tool, which can do the actual rebalancing of moving partitions.
Are you running on a schedule basis or?
So right now it's on demand basis, but we are going to make it automatic. It's just, our confidence level has increased now, so we're going to run it in cron fashion. Sorry.
Two questions. Are you running on physicals or virtuals for your Kafka infrastructure?
So we're running on physicals for most of our infrastructure. We started looking into virtuals right now for the multi-zone data center, and we're going to present that next time we are on stage.
The second question is, are you using compression on your topics?
We are.
Yes.
Yeah.
Yes, we do compression on our Kafka clusters.
Do you want to give the snappy versus gzip?
Oh.
Yeah. So we did some research and did benchmarks on what kind of compression works. I don't remember exactly the outcomes, but yes, we are using compression.
So we're out of time actually. Take questions.
Yeah. So all right, we are here to answer all the questions. Yeah.